Thank you. So as a roadmap, while it may look like I have two separate talks based on that title, in many senses I do. And so in the first half, we're going to take a look at some broad strategic considerations of what should we be doing with Neuromorphic and use that to then help drive where should the field be going, given what's going to be announcing a very exciting large-scale state-of-the-art system that we're going to expand. So to set the context for the first half of strategic considerations, in 2021, so a few years ago now, Sarah Hooker wrote this perspective paper, The Hardware Lottery. It's a fantastic read. I highly encourage it if you haven't read it previously. And it starts off with this just broad exploration treatise on just computing and technology in general. And it notes that that science, that technological progression is biased, that we follow best practices, things that have been ingrained, taught from our predecessors based upon existing tools. That's kind of understandable. That happens. But it has this implication, the namesake hardware lottery, that really it's an idea lottery. It looks at, as we consider the superiority of one idea versus another, that often that conclusion is biased. It's driven by some enabling concept. It's not that one idea is superior than the other, but there's enabling concept. So it can be looked at from either perspective, hardware or software, even though the name's hardware lottery. But so it looks at, is one idea better than another? Or do you have enabling hardware that made it better? Do you have enabling software that actually made it better? And she goes through a historical narrative, going all the way back to Babbage, looking at as soon as we could build mechanical computers, there's kind of been this notion, this entanglement. And so even has this perspective that understanding that there's time lags, there's how do you synchronize these different efforts, that hardware design has often prioritized, let's deliver on commercial use cases. We need to enable technologies now, making the next generation ideas a secondary consideration. Grounding that a little bit more, let's bring this into the field of neural networks, not just computing at large, but using deep neural networks as an example. She identifies, if we look at the history of backpropagation, it's been invented algorithmically multiple times, 1963, 1976, 1988, coupled with convolutional neural networks in 1989. But then it was still a few decades later before we get the AlexNet moment, the innovation where GPU hardware acceleration on the right half of this timeline all of a sudden made deep neural networks, backpropagation, a promising research direction, even though it had been around for decades. And so really point being, it shows that this entanglement, this coupling of research ideas really, as we compare what is the right pursuit, how should we innovate, what should we go after, there's really coupled dependent considerations. They're not independent ideas. Now, with that concept, with the notion of ideas being coupled, that they're not independent, that we have to assess one over another, as a quick context setting, game theory is the mathematics of strategic decision-making. It's the mathematics of how should you reason when you have interdependent decisions. So unlike optimization, where it's finding the best parameterization for a fixed scenario, in this case, the decision-making is dependent upon the decision-making of somebody else. My decisions are dependent upon someone else's decisions. It's not just a fixed optimization. The mathematics goes back to the 1920s. Emil Varel, John von Neumann, they were doing work in the 20s. Seminal book went to John von Neumann in 1944. Cartoon form, nuances don't matter, but just to kind of familiarize some of the situation I'm going to unpack in a moment. Bottom left, most common game example anybody was familiar with, Prisoner's Dilemma. You have these two people being interrogated, asked independently questions. This matrix on the left is just saying, hey, these are the rewards based upon what they say, their joint outcome. What they both say depends on what the outcome is. There's multiple ways, lots of richness for how do we model scenarios, lots of relevance. But given that, let's look at neuromorphic computing from a strategic perspective. Let's consider coupling decision-making. So I'm going to give two vignettes, two examples. In this first one, let's look at the Colonel Blotto game. Game theory has lots of fun analogies, lots of vignettes for what the names of scenarios are. This seemingly simple game goes back to the 1920s by Borel. It's a zero-sum resource allocation game. And so it's this idea that you have two opponents. They're deciding how to allocate resources. Based upon the name, it's two military leaders. They're putting troops to a battlefield. That's what the bottom left is showing. Simplest formulation just says whoever puts more troops at a given battlefield, they wins that outcome. That's what the bottom right shows in cartoon form. Despite that simplicity, there's a lot of richness that this becomes an NP-hard decision-making problem. We can scale this up based on how complex a battlefield do you have, how many decisions, how many resources do you have, are they finitely divisible? Is it a richer outcome interaction than just majority wins? Is it repeated play? Lots of nuances. And people have applied these things to games like how should politicians allocate resources for constituents, even R&D investment. What scenarios should invest in? What are patent outcomes? Scenarios like that. So taking that simple construct, let's look at computing at a high level. Let's, in this case, in picture form here, let's think about these battlefields now as computations or workloads. What are we trying to compute? And at this level of abstraction, let's start by looking at CPUs versus GPUs. So in this formulation, a CPU is a general purpose processor. It's pretty okay at everything. So nominally just said, hey, we can do every workload. GPUs specialize in specific workloads. They're pretty good, really good at certain things, but not everything. This leads to this artificial outcome where, well, when everything's treated equally, CPUs slightly win because there's workloads you need to do, GPUs can't do. But we can add in weighted battlefields. We can start saying that some workloads are important. That's for whatever reason, monetary, computational interest, needing to solve tasks. Once we start adding weights with the numbers in the little computer monitors, now the GPU can be shown as advantageous because it's really good at specializing in these certain tasks that are deemed important. Well, what about neuromorphic? So we can agree neuromorphic isn't better at every computation. No free lunch theorem will show us that there's no ideal perfect solution for everything. Like a GPU, neuromorphic can excel at some things. It's good at some things. It's not as good at other things. And so compared with the CPU, I arbitrarily made it exact same outcome. I can show with a different distribution. So it's no longer just this dominant, really good at two workloads, but it has a similar distribution. It's good at a few things. It's bad at a few things. This little pairing, it makes, it can outperform a CPU. But when we compare to GPUs, now we're looking at a similar strategy, but worse, is not the key to success. This is like playing the lottery numbers that won previously and hoping to win again. And there's a lot of pursuing this concept that what GPUs and deep neural networks have been great at doesn't mean that's the right strategy for neuromorphic, just because it's a neural network, that we need to think about what should we be applying neuromorphic for. And this resonates with what Terry Sosnowski said on Monday in his opening keynote when he was talking about how should you get into an existing dominant field, not by taking on the big existing incumbent, but looking at what do you do well and not just copying the incumbent, but doing it worse. As a second perspective, so co-design has been mentioned a little bit here and there. This is this notion of the mutual benefit of coordinating design choices like layers in the technology stack. In this case, decisions are independent. Again, otherwise this would be an optimization. It'd be just finding the best you can do with an existing configuration. But instead, it's working together, trying to decide what can you mutually do better. Casting neuromorphic computing and thinking about neuromorphic computing as a co-design problem, we could look at multiple layers. I'm going to look at the algorithm architecture stack rather than going down to kind of devices architectures, but you could consider this in other ways. I'd argue that we can look to a canonical game called the Stag Hunt to get information about what neuromorphic computing as a co-design game can tell us. So in this kind of base formulation, it has this back narrative where two hunters can team up, they can bring in a higher value stag, or independently, they can get hares. Importantly, the bottom right shows the relationship structure of the outcomes. Otherwise, different ratios, different relationships change the dynamics, change the games. So importantly, the high value stag in the top left, stag, the A pair is more valuable than the hare. And then there's some nuances around if they don't cooperate, how they split the smaller value items. I mention this because I think we can use this to look at the interplay of algorithms and architectures. We can think about some of the questions around, do we need an existing algorithm, a known spiking neural network algorithm with theoretical advantage to drive hardware? Or do we need an architecture to drive and spur innovation in theory? Can either be pursued without becoming a lottery for the other. So a few few analysis of this. So starting at the front here, this is just base ratios, kind of a canonical stag hunt relationship. So when we look at this, players left and right, one player is an architecture player, one player on the top is an algorithm player. So how should the architecture player, algorithm player play together? In this case, should they both be designing spiking neuromorphic? Should one of them be doing artificial neural networks, just abstractly? Importantly, though, what this identifies is that despite the fact that the upper left, 5-5, is the most appealing, most mutually beneficial outcome, the mixed strategy equilibrium solution actually says that players are incentivized to play spiking neuromorphic 1/3 of the time, default to going artificial neural networks 2/3 of the time. You don't default towards spiking neural networks. So promise of spiking neural networks, it's large, but it doesn't overcome the less risky take the known outcome. So what about if we have breakthroughs? What if we have some great spiking neuromorphic breakthrough, whether it's algorithms, architectures, driving the field, big left arrow from the top left. That actually has the unintuitive expectation that it actually drives down spiking neuromorphic entirely. The plot on the right looks like you sweep up, increasing those values, putting numbers rather than just turquoise arrows. X-axis is what is that value? Y-axis is how often do you play that strategy? So it actually goes from playing it 1/3 of the time to actually dominating it out. If you have a 10x increase, 100x increase, you don't even play the spiking neuromorphic approach anymore. Well, what about, let's compromise. Rather than just seeking solely to advance spiking neural networks, what if we support artificial neural networks along the way? We know they exist, we know they work well, they're great. In this case, kept the ratios the same. Top left, I bumped those up to 10s, unlike the 5 from before, just so that way we have some wiggle room to sweep over this ratio of 3 to 9. Really, this is getting at what's the ratio of spiking neural networks, artificial neural networks. There's a scenario, the formulation says risk dominance prevents spiking neuromorphic from ever overtaking artificial neural network. It caps it at 0.5. Best case scenario, if spiking neural networks are at 10, artificial neural networks at 9, you're 50-50. So we never just can strategically drive innovation to say, let's pursue neuromorphic. So with that discouragement, as you may think, let's now look at, well, where are we in the state of large-scale neuromorphic? What can we do? So as a brief motivation for scale, is a few fun vignettes from multiple fields. Top left, just computing at large. We've been tracking what is the most capable, what is the largest supercomputer in the world since 1993. Top 500 benchmark looks based on the LinPack. How can you solve linear equations? Marching towards exascale. We can say, hey, here's the most here's the most powerful supercomputer, solves this problem. That coupling of what can you do with scale has fun examples like the bottom left. People look at the advent of stealth technology, the stealth fighter. There's a 1964 theoretical paper looking at how can we do this inverse electromagnetic pulse propagation. In 1975, DARPA had an effort to try and instantiate it, but computers were computers of 1975. So the visualized F-117 stealth here has this very boxy, not smooth like we see in modern technologies because they could only do 2D computer modeling. They didn't have enough compute to do 3D to get nice smooth scaling. And other examples, top right, as a neuroscience example that people in this room probably know far better than me. 1971, place cells were discovered in hippocampus. But then many decades later, grid cells were able to articulate due to an example of scale that the complex firing patterns, this big sphere of activity was hard to discern with the earlier exploration. So increased the experimental box, got larger recording patterns, large simulations, increased scale. We're able to identify and understand the place cell phenomenology. And then just kind of a reminder from in these kind of the origins of deep neural networks, we step back, look at this June 2012 articles, New York Times and others. As Google was making these breakthroughs with deep neural networks, they were actually throwing 16,000 GPUs at the problem to be able to find cats in YouTube videos. So, all right, getting back to neuromorphic here. So as a quote, the neural computing phenomenon is truly amazing. Over the past 3 years, there's been a veritable explosion of interest in neural networks and neurocomputers, even though its foundations have been around since the 1940s. And an unusual character of neural computing is its interdisciplinary nature, spanning neuroscience, cognitive science, psychology, computer science, electronics, physics, mathematics. That's very evident of our meeting right here. This spectrum of disciplines engaged in neurocomputing research means that much of the current literature is scattered over many sources. Surge of interest in neural network applications and models over the past 3 years has led to the development of special neurocomputers and neuroprogramming environments designed to support the execution and programming of artificial neural networks. So you may be thinking back, okay, last 3 years, nice. What systems is he referring to? Was this Spinnaker 2, Loihi 2, Brainscales 2? This is actually a quote from 1990 from Philip Trelevin. And in fact, as we take a brief reflection, kind of looking back at what has the field been doing over the decades, how does that relate to what we're pursuing now? What is the same? What is different? This kind of dichotomy shown on the right from 1995, there's been a longstanding pursuit of looking at, can we use standard chips? Do we need specialized neural chips? Are we looking at analog? Are we looking at digital? Are we looking at hybrid? Are we looking at accelerators? Are we looking at a multi-processing approach? That a lot of these ideas are decades old at this point. And at the same time, people have also recognized from the very beginning of the neural network era that to fully exploit the potential, that's also necessary to look at enabling hardware implementations. A few brief fun examples. We don't have time to go into a full history, but looking back to the Mark I perceptron of 1958, some blurry pictures here, but some fun anecdotes. If we look at the bottom left here, preceding MNIST, going back to the 1958, we're still trying to recognize digits, just rather than being handwritten. We have a massive printed digit on the wall that he's imaging with a camera here. This entire rack is only 8 neurons, and on the bottom right, we have the fun, he's pulling out the weights of the system. That right there, he has the potentiometer setting weights. So, program the weights physically. Jump forward a few years, we have Bernard Woodrow's efforts in the 60s looking at resistors, electronically adjustable resistors. This was a fun example to include also because you may or may not be aware that it was actually a commercial offering. There was an attempt to have a commercial neuromorphic offering in 1962 to 1965. He never could get learning really to work, so the company didn't work well, but he also had the early, very blurry, but the top right is showing, looking at, call it what you want, cart pull. He has a mechanical broomstick that he's trying to balance with neural networks in 1962. On the right here, Robert Heck-Nelson has this fun book looking at neurocomputers built to date in circa 1989. Goes back from some of these early 1950 efforts to some of the 80 efforts. Some of these are commercial, some of these were commercial, some of these were just experimental. Fun example of scale, spans, whether we're looking at specialized processing, whether we're looking at how exactly we're trying to get there. The plot on the left shows that some of these same concepts we're looking at now have been around for a while. The systolic array for neural processing is well before Google revived it for the TPU, looking at kind of the complexity of node complexity scaling. Lots of rich questions have been around since 90s and on. Also, rich wealth from Heck-Nelson, looking at applications. What are the applications for neuromorphic? Wall of things here, don't expect you to realize them, but they have some surprising examples that we're looking at again today, looking at autonomous vehicles, looking at language translation, looking at defense, looking at lots of fun examples here. This paper is also from 1989, but this don't have time for everything, unfortunately. There's many, many more neuromorphic architectures than we would think about at all levels of maturity. This was me just trying to grab every name I could find. There's fun examples like just great names like the Wizard neuromorphic processor. Great. So bringing us back today to recent efforts. So many people are aware. So at Sandia, we've been partnering, pursuing large-scale neuromorphic systems over the last couple of years, as well as Department of Energy, Lawrence Livermore National Labs, Air Force Research Labs, Spinnaker efforts from University of Manchester, now moving on to TU Dresden, some international efforts. And we're excited, as many people may have heard last week, to announce that we have now, in partnership with Intel, reached a billion neuron system. So top right, hollow point. So it's a little bit of a build-up, a fun animation. Kudos to Intel. This is only snapshots because I didn't want to risk whether or not a video would embed and play. But so this is using the low-E2 processor. So low-E Gen 2 processor has 1 million neurons per chip. Scale that up to 32 chips per card. String up 3 cards in a row. We're up to 96 million neurons. String together several of those into a nice, exciting box, and you get 1.15 billion neurons in a 6U rack. Has some system specs associated with that. So you did the math there. It's 1,152 low-E2 chips. Each of these equates to, or the aggregate of this equates to over 140,000 neuromorphic cores. So really, this is an entire cluster within a 6U rack. It's a phenomenal just feat of engineering, running at 2,600 watts. Capacity-wise, this is 1.15 billion neurons, up to 128 billion synapses. In the bottom left, trying to map that towards, let's relate this to what computing capacity is this. This is idealized, can do 380 trillion synaptic operations per second. This is, there's different communication speeds, whether we're talking chip to chip, core to core, board to board, different, just how do we shuttle data around system of this size? Mapping this towards traditional systems, this is a 20 petaop system. So it's a very capable system just in terms of operations, but bringing that into what has become more of a prominent characterization relative to GPUs, other accelerators, performance characterization has brought this at 15 tops per watt for 8-bit operations. This is a brand new system, so admittedly the depth to that characterization is limited at the moment. So really it's looking at, can we take a multilayer perceptron, but following my earlier emphasis on strategic considerations, this is not just taking multilayer perceptron, but let's look at what advantages this system can offer. Sparsity. So let's look at connection sparsity. Let's look at activation sparsity. Let's, in particular, so we're working on characterizing a 10-to-1 reduction. So with that, that's how we're able to get the 15 tops per watt. We're working on a much richer, much more interesting applications. As the first step towards that, Felix Wang at Sandia has been doing some great work. You missed his poster yesterday on stacks. Don't worry, he has a tutorial tomorrow, so you can still have a chance to learn about stacks. So he's been using stacks framework to try and look at how can we scale and map reservoir networks to the system. Part of our rationale there is working towards how can we partition and map problems to a system of this scale, because that's an unsolved problem. It's very challenging, but also using this as a starting point where we can scale up and then we can control properties. It's a spatially dependent reservoir, so based upon distance of where the neurons are, regulates how connected they are. It became a roughly 25 synapses per neuron, and then controlling the partitioning. So splitting it into 4,096 partitions, but then looking at where do we place those partitions? Are we dividing those partitions very densely using 120 per chip, or are we going to put them on 4,096 different cores? How are we going to vary that while keeping the workload fixed? That's a parameter that we can tune later. If we don't want to keep the workload fixed, we can vary that. Blue, can't really see anything here, but what that's getting at is, it's very hard to map systems of this scale. So this is just a spatial placement. Blue dots are all different neurons. There's a lot of black lines that you can't really see, but those are the different partitions. So this is really just getting at, let's have neurons that are connected, that are close to one another. Let's put them on the same part of the system. Let's not make this hard on ourselves. And then the right, apologies, it's really hard to see. There's some really light blue dots there, but this is a subsample of 60,000 neurons. Even just reading out outputs when you have a lot of neurons is hard. So early days, but exciting on what we can do with the system. So doubling back down on Treleven's quote, over the past 3 years, there's been an explosion of interest in neural networks and neural computers, even though its foundations have been around since the 1940s. And to deliver on that promise, scaling advances are supporting neuromorphic hardware, algorithmic innovation, simulations. We've seen that across the last couple of days. But then looking at the first half of my talk, I think some strategic considerations should guide that while we are able to make big systems, billion neuron systems, we need to be strategic and intentional about what we can do with them. Let's pick the right workloads. Let's try to understand what is neuromorphic good at. And that offers an exciting opportunity to try and identify what are those workloads. How do we do the infrastructure to get them there? When is there an advantage? Is it under certain scales, conditions, problems? And then just as a plug, Sandia Labs has 5 workshops tomorrow. Unfortunately, for the last session, you have to choose between which of the 3 Sandia tutorials you want to go to, but ranging from simulation tools to software stacks to a hardware emulation, we've got a full stack. And then this is just at Sandia. ASCII Red on the left was the first teraflop machine. It was the largest HPC in the world at the time. We take that very seriously, and so we're excited to see what we can do now that we have the largest neuromorphic system as well. Thank you.